Okay, so a very good example of a drainage basin is the Snake River drainage basin that we have here in Idaho, and a little bit of, I guess, Wyoming, Oregon, Washington, a little bit of Nevada even. So the Snake River drainage basin, or the Snake River itself, pretty much starts in western Wyoming at a very high elevation, so about 8,100 feet. That's going to be close to 2,600 meters. Um, and then as it goes through its path, as you're seeing over here, it's going to start lowering in elevation. So here in Boise, we are somewhere around 2,600 feet. So it's already lost easily, what is that? Boy, math is hard. Over 5,000 feet in elevation through that path. And then eventually it's going to get low enough to about 125 feet here in Kennewick in Washington, where it merges with the Columbia River. So we call that lowering in elevation a loss of potential. So the river has more potential as it's higher up in the mountains, and then it loses potential as it gets lower and lower in elevation. So you can think about it as it has more potential of getting down because it's higher up, and it has less potential of going down when it's already fairly low, if that makes any sense. So it has more potential of carving through the rock and wanting to get to its goal, to its final place, if it's higher up in the mountains where there is more slopes, more gradients for it to get down to or from. And then it has lower potential when it's lower in elevation, where there's less slopes to get down from. Okay, so as I was saying, that potential is going to have to do with the gradient of the landscape itself. So the gradient itself is going to be rise over run. So you are, for the most part, in a river, unless it's a very weird condition, you're going to go towards lower elevations, right? You're going to flow downhill, not uphill. So in a river, the gradient is going to be the highest elevation, so let's consider A as the highest elevation, minus the lowest elevation that you're looking at the end of the river, so that would be B in this case. And then that we would divide over the distance between A and B. That would be the overall gradient for this specific river, which is the Fox River. Okay? If I just want to know what the gradient is between A and this fork right here, then I would say, what's the elevation at A minus what's the elevation at the fork, and then I divide that by the distance between A and the fork. That would be the gradient for that specific stretch of the river. Okay. So there is something that we call the longitudinal profile. Wow, I can't speak today. But the longitudinal profile is going to have to do with that relationship, that the higher you are in elevation, which in this case we're going to call A up here, the greater the gradient is going to be. And then the lower you are in elevation, the closer you are to the base level or the place where the river drains to, then the lower the gradient is going to be. So as you're seeing in this plot right here, the distance, or like the beginning of the stream, so that would be distance 0 pretty much, is going to have is going to be at the highest elevation, and the gradient is going to be the highest. So that slope of this line is the highest at the beginning of the stream. And then as you get further and further, meaning as the stream grows and grows, the elevation is getting lower, and the distance from the beginning is getting greater, right? And you're seeing that that slope is now a little bit more shallow. So basically, once you get to the end, that slope is almost none. It's almost completely flat. And it's also obviously the end of the stream, so it's going to be the farthest distance. And the elevation above sea level is going to be close to 0 if the base level is the ocean, as it is in this scenario. If the base level is a lake, it doesn't necessarily have to be 0. It could be however high the lake is, but it's going to be close to that base level elevation. Okay, so if you were to take a cross section through the river's width, if you would, that is something that we call the river channel form or the river channel shape. Okay, so that's going to change throughout the river's length with the gradient that the river is at. So what the slope is at where the river is flowing. So as two examples that I have here, you're seeing that where the river is in highest elevation, where the gradient is also the highest, you're going to get a pretty narrow river with a V shape, as you're seeing up here. So at that point, high elevation, the river is going to have a lot of potential and is going to want to get down as soon as possible. So it's not going to have a lot of time to make a broad shape, but rather it's going to be fairly narrow V shape. But it's going to go very fast. For the most part, the velocity at those high elevations tend to be fast. And again, that's due to the slope. And also because it is going so fast, it's also very erosive, meaning it's able to take any sediment that has been weathered out on the sides and transport it to a different place. So it's going to be able to take any sediment from the sides and transport it further. If you're going to look at the river channel shape further down, where the gradient is not very high, so it has a low gradient, that river is no longer going to have a narrow V shape, but it's rather going to have a broad shape like you're seeing down here. So because the river doesn't have a lot of potential, the slope is fairly shallow, the river can take its time and meander around and kind of just go slowly in whichever way it wants to go. So now it's going to be a lot slower. It's not going to be able to erode as much stuff, but rather it's going to deposit many of the particles that it eroded further upstream. So again, you have more erosion up here, less erosion down here. And with less erosion, you also have more deposition down here. So you're seeing here that the river channel is fairly small, but the floodplain is fairly large. That means that the river can change its course through time because it has a lot of time. It doesn't have a lot of pressure to get down to a specific place. It's already fairly low slope, so it doesn't have a lot of pressure. So many times the river channel can go all the way down here, or maybe all the way down here, or maybe, depending on the year, it might be so wet that the river channel overflows and it floods into this big floodplain, as they're calling it. So the floodplain may be an actual floodplain where if the river floods, it goes, like the water will go all the way to the ends of the floodplain. But it could also be an area where the river changes course too. So again, over thousands of years, the river could go from where it is right here to a different place over here or whatnot. So good examples of this V shape versus broad shape for the different river channel forms are going to be, the Boise River is going to be a very good broad shape river channel, right? So you're seeing the Boise River, we come into the Treasure Valley, which is a very shallow slope area, and we have a very large extent of land. The river is not constrained necessarily by two banks, and so it has a very low gradient overall and a broad shape. But if you think about Riggins, for example, if you've been to Riggins, the salmon river that flows there, it flows pretty fast. That's partly why you have rafting in that river. And it flows, or the sides of the river have a very V-shape like shape. So in the Riggins area, you have very high mountains that are coming down into this very low valley. And so the river has a very high potential going into very low potential. So Riggins, or the Salmon River, I should say, is a very good example of this V shape, and then the Boise River is a very good example of this broad shape. So going back to the beginnings of our class where we talked about different mechanisms that, made rocks, if you would, and then also eroded rocks, moved them around, we know that rivers are the major mechanism through which rock is going to be eroded, transported, and deposited elsewhere. So they're major players, or not necessarily rivers, but any surface water are going to be major players within this rock cycle, actually, or not necessarily the rock cycle, but the cycle of transportation, weathering, and whatnot. So we know that volcanism, for example, or even just intrusive igneous rocks being made, are good makers of the rock underneath. We also know that through metamorphism and plate tectonics, we have the building up of mountains. But it is rivers and streams and gullies and all that surface water that in the end actually erodes the land that has been lifted up or has been deposited through volcanism. And then as it erodes it, it transports it elsewhere and deposits all those sediments in a different place. Those sediments that are deposited may be deposited far enough that they may remain sediments for a long time, or they might be deposited in a place where they can solidify and lithify and then become rock. So if we're looking at this diagram over here, the rivers and the surface water overall are going to be, again, big players within this weathering and transportation part of the cycle. Okay? So the ability of a river to erode material that, has been uplifted through plate tectonics or has been deposited by volcanism or even other sedimentary moving forces, if you would, that ability is going to be a function of the stream velocity and of its discharge. So that erosive ability, again, is going to be a function of stream velocity and discharge. So the stream velocity is going to be basically how quickly is the stream flowing through its complete longitudinal profile from its source. So if we think of this diagram, the source would be over here, to its outlet, which in this diagram again would be over here. So how fast will the stream flow through its longitudinal profile, which in this case again is this, from the source to its outlet. And then the discharge is going to be the amount of water that is passing through a particular cross-sectional area of the stream through time. So the discharge itself, the formula for it is going to be velocity times the area. And again, discharge is going to change depending on what cross-sectional area of the stream you choose to measure. So let's go with terminology really fast. Discharge we call Q. It's always going to be Q, a big Q, capital Q. And it's going to be measured in units of meter cubed per second, or many times also as cubic feet per second. So for the Boise River measurements, for example, you'll find it as cubic feet per second. So again, that Q is going to be equal to the velocity times the area. And so if we were to choose the cross-sectional area as this right here, where the outlet of this particular diagram is at, then the velocity would be how fast that water is moving through time, and then how much of it is moving, I guess. And then the area is going to be the area of this particular part of the stream. All right? So again, discharge is going to be velocity times area. And be sure that I'm going to ask that formula in quizzes and in exams. So as we have said before, however, that velocity is going to change due to the cross-sectional area that you choose. So if it's higher up in the stream gradient, it's for the most part going to be greater velocity. If it's lower in the velocity gradient, meaning closer to its outlet, then the velocity is going to be lower for the most part.